Hello, and welcome to this presentation of the AiZynthFinder software for retrosynthesis analysis. My name is Samuel Genheden, and I'm a scientist at AstraZeneca working as the main developer and maintainer of this codebase. And within this presentation, I will show you the capabilities of the software and make a deep dive into the codebase. So this is the content of the presentation. We'll start with an overview of the retrosynthesis problem, and even though it might be familiar to some of you, it will highlight my perspective of the retrosynthesis problem, which has informed how the software is structured and coded. Then I will give an overview of the codebase, the most important packages, modules, and classes. Then we will look at how these classes interact with one another in the Monte Carlo tree search, and later in the analysis stage. We will finish off with looking at some other bits and pieces that might be of interest. So, retrosynthesis analysis. So it's a computational method that starts with a target molecule, and then we want to know how to synthesize this molecule. So we pick a disconnection, we break one or a few bonds to make precursor molecules. And there are many bonds that can be broken, resulting in different precursors. And then we do this iteratively until we have reached a stop criterion, which is typically that we have reached, we have found precursors that are in stock. So this can be compared to games, and algorithms to solve this problem has been inspired by game theory research. The thing with retrosynthesis is that compared to games like chess and Go, we have a much wider search tree. At each point in the search tree, we can make many disconnections. There are more than 1 million different types of reactions, and even though not all of them can be applied in each stage, we have a very wide search tree. On the other hand, we have a very shallow search tree. We don't want to do hundreds of steps in order to synthesize our molecule. We maybe want to do around 10 at most. So this highlights what we need in order to solve this problem. We need to define the disconnection rules, how to break bonds. We need to decide at each stage what rules are best, and we need an effective search algorithm because it's impossible to enumerate the entire search tree. That's way too ineffective. Okay, so let's start with how we define the rules. And in AiZynthFinder, we have a template-based retrosynthesis model. So we extract chemical transformation rules from reaction databases. Here we have an example reaction from a database where this nitro group reacts with this iodine, forming this molecule. And this can be represented in a computer using a reaction template. We take the reacting atoms and a certain amount of the environment around it, which we can encode as SMERCs, the long string at the bottom, which is difficult perhaps to read for humans, but for computers it's a very compact format. And we have done this. We have extracted a couple of 100,000 of reactions. So these are a bit old statistics. They are a few years old, but we can extract these reactions from commercial databases, from patents, and of course from internal reaction databases as well. And then we need a way to determine which of these templates to apply at each stage of the search, what templates are most likely to be useful. And in AiZynthFinder, we use a simple neural network that predicts the probability for each template given a molecule. So we start with a query molecule, we encode it as a bit string, a fingerprint, which we then feed to a simple neural network, which we call an expansion policy, which gives a ranked list of all the templates. And we typically keep the top 50, which we then apply onto the target molecule, producing different sets of precursors. And you can see the reference at the bottom. Applying the templates given by the expansion policy is not always a great idea, because the expansion policy doesn't know a lot about chemistry. It doesn't take all of the environment of the reaction into consideration. And therefore we train another neural network to filter unfeasible reactions. So given these reactions given by applying the template, we ask which of these are feasible, and we can determine which are unfeasible, and we just simply remove them from the search. So this is a quick way to add some extra chemical intelligence to the tree search. It's not 100% effective, but in certain cases, for instance, for selectivity issues, it is quite good and adds onto the accuracy of the search. And then we have the search algorithm itself, and we have implemented a Monte Carlo tree search algorithm that iteratively selects a node in the search tree for expansion, and a node here is a super node consisting of one or more molecules that potentially can be broken down into other molecules. And after we have selected a leaf node for expansion, we use our expansion policy and our filter policy to add new nodes onto the search tree. Then we do a rollout, which is a way to estimate how good it is to continue along the current direction of the search. And this is done by sequentially adding more and more nodes to the tree until we reach a terminal node. And finally, we have an update procedure where we update the statistics of the search tree, propagating the score of the terminal node up through the tree. And we repeat this a number of times or until the search time is up. And we select nodes and we score the routes based on upper confidence bound statistics. You have the formula here, I will not go into it much, but you can read about it in the literature. But we have one term for exploitation and one for exploration. And the Q here is an accumulated reward. So when we reach a terminal node, we can calculate the reward, the cost of that set of molecules, which is a function of the depth, how many steps it required to reach that node, and the fraction of the molecules represented by that node that are in stock. If you want to know more about the math and so about Monte Carlo research, I suggest you read the literature. Now I will briefly touch upon a few other features available in AiZynthFinder that is part of a post-processing set of tools. And one of them is root scoring. So we have a framework for adding scores, and these are the ones that are currently implemented. So we can score and rank the roots based on the Monte Carlo reward functions that I showed in the previous slide. We can score based on number of reactions, precursors, and so. And then we also have a root cost, which is a recursive function taken from a Chematica paper that recursively scores a root based on the cost of molecules and yield and the cost of reaction. Then we can also score based on just the sum of the cost of all the starting material. The two final scores here assumes that the stock has price information. And all the scores are computed when the root is predicted. Then we have the capability to cluster roots as well. And this is based on a machine learning model that can predict the distance between roots. And the distance encodes what molecules or reactions need to be substituted or inserted to turn one root into another. So it's a recursive application of chemical similarity matching. And it's a very fast method, and you can read about the details in the reference. Okay, but let's dive into the code now when we have a common understanding of the retrosynthesis problem. Okay, let's look at the top level packages and modules in the AiZynthFinder package. So it's a Python code base. Perhaps that doesn't need to be said, but anyway. So at the top level, we have a few packages shown here that are the most interesting. We have the AiZynthFinder Chem package. We have the context package, the search package, and the analysis package. The Chem package contains chemistry routines for molecules and reactions, and it's basically an interface towards RDA kit. Then we have the context package, which contains everything that is necessary for the search, so configuration, policies, stocks, and so on. Then we have the search package, which encapsulates different search algorithms. And we have the analysis package, which contains a few helpers for doing analysis. Then we have 5 other packages that are of less interest for this talk. I will not touch upon them more than this. And then at the top level, we also have a AiZynthFinder module, which contains a Python interface to root and precursor prediction. So all the search and the context is bundled together in a nice user interface. Then we also have a reaction tree module, which contains a data structure for representing synthetic roots or reaction trees, which is a data structure that pops up in a few different places throughout the code base. So let's look at the AiZynthFinder chem package a little bit more. And as I said, it's mostly wrappers around RDKit objects and routines. So we have a molecule class that has all the things you need to work with molecules. So smiles, it has a reference to the RDKit molecule object, INCHI keys, fingerprints, etc. And most of these properties are and routines are evaluated lazily, so they are only evaluated when you need them, and then stored for easy retrieval. And this is a way to speed up the calculations. The molecule class has two child classes: a tree molecule class that is a molecule in a search tree, and it has a parent molecule. Then we have the unique molecule, and the difference between a unique molecule and a molecule object is that a molecule object, two instances of that class, can be compared based on the INCHI key. So two instances of the molecule class can be equal if they have the same INCHI key. But that's not true for the unique molecules. You can have two instances that are not comparable. Then we have a reaction superclass, which is a mixing class, and it has two child classes mainly for retrosynthesis, one retroreaction and one fixed retroreaction. And the difference between these two is that the retroreaction, the reactants are created by an application of some sort when the reactants are needed. So they are not created upon instantiation, but for a fixed retroreaction, they are basically there from instantiation. And the retroreactions in turn has two child classes, a templated retroreaction and a smile-space retroreaction. So the templated retroreaction is the one that is used most because it creates the reactants when needed by applying a reaction template. So this slide highlights the differences between the retroreaction classes and also shows the difference between a tree molecule and a unique molecule. So a retroreaction, that class is used in a search to expand the search tree and create new molecules. So it has a mole object, which is a tree molecule, and upon need it will create reactants, new molecules that are also of the tree molecule class. A fixed retroreaction, on the other hand, is used in post-processing of roots, synthetic roots, where the mole and the reactants objects are unique molecules that are there upon instantiation, for instance, reading a root from disk. In both the retroreaction and the fixed retroreaction, the reactants property is in fact a tuple of a tuple of molecule objects. And the reason it's a tuple of tuple is that a retroreaction can create more than one set of precursors. And especially if it's a template based, it's ambiguous with regards to the template application. So a template applied on the same molecule can produce different sets of precursors, and that's why we need to have it as a tuple of tuple. Right, the next package that I will talk about is the context package. So this has everything needed to make predictions and to guide the search. And it constitutes a number of sub-packages shown here. So we have a policy subpackage which contains expansion and filter policies, a scoring package which is this framework for scoring routes that is currently only used in processing. Then we have a stock package that contains stock query algorithms, and finally we have a config package. So let's start with the policy package. So many of the classes in the context subpackages are container data structures, and the expansion policy class shown here is no different. It holds a number of items and capabilities to select one or more of those items. Then it has a load function and a load from config in order to add and load items from some place like a disk, a serialized item. The items that the expansion policy holds are of the type expansion strategy. So this is an encapsulation of an algorithm that produces precursors, or rather it produces retro reactions. And the one implemented currently in AiZynthFinder is called a template-based expansion strategy. So this uses a Keras-based neural network model that I talked about at the very beginning of this talk to prioritize templates and give templates or retro reactions based on those templates. And the relationship here between an expansion policy and expansion strategy is own or has, which is symbolized by this diamond. We will come back to the get actions method, which is the way that the expansion policy is used. We also have a filter policy class, which has a similar interface to the expansion policy, but it holds filter strategy classes. And currently there are two available. We have a quick Keras filter, which is the feasibility filter I was talking about at the very start of the presentation, and we also have a reactance count filter. I will not talk so much about that, but that comes out from a GitHub issue. So a user of the software requested a filter like this, and it was very straightforward to implement. Okay, and the filter policy has an apply method that is used to for using the policy. And the thing is, get actions, it returns a list of retro reactions encapsulating a chemical reaction in the retro sense that we looked a few slides back. These retro reactions are eventually passed as input to the apply function of the filter policy. And if the retro reaction is okay, the filter is okay with it, it's not unfeasible, for instance, nothing happens. But if the retro reaction should be reacted by the search, then the filter policy will raise an exception, signaling that this reaction should be discarded. So that's the relationship between those classes. Then we have the stock package with a stock class, which has a similar interface to the policies just shown, because it also is a container, and it holds items of the type stock query mixin. And we provide two implementations of that class an in-memory INCHI key query, which holds a list of INCHI keys in memory. And we have a MongoDB INCHI key query, which holds a database, a Mongo database of INCHI keys. And the stock is used with the contains method. So you write my molecule in stock, and it will call the contains method, and the contains method will go through each of the selected stock query mixin and see if the molecule is in one of those items. It also has a few extra things in the interface. It has, you can query the amount and the price if your stock holds that type of information. You can also set stock criteria, which are generalized criteria, like number of carbon atoms or maximum price and things like these. The last package I will talk about in the context package is the config and the configuration class. So this basically brings all the other container classes together. So it holds a stock, expansion policy, a filter policy, and a score collection class. And it also holds a dictionary of atomic settings called properties, which are used to control the search, the setup, and so on. And you can load this configuration from a file or from a dictionary. And typically you have a YAML file on disk where you can set the properties. So these properties will correspond to the properties attribute of the configuration. And then you, in the YAML file, you also specify the policy, which will go into the expansion policy, filter, which will go into the filter policy, stock, which will be loaded into the stock. So this is how it is brought together, all the things in the configuration, and this configuration class will then be passed around to the various parts of the software that is needing it to perform various tasks. Okay, then we have come to the last part of the code overview, which is the AiZynthFinder analysis package, which mainly contains two classes for helping out with post-processing. So we have the tree analysis class, which knows how to extract roots from a search tree and sort them. And it can also extract statistics about the search tree. Then we have the root collection, which is a container of synthetic roots and associated structures like images and dictionaries. And you can use this collection to perform various analyses of the roots, like computing scores or cluster the roots. Okay, now when we have seen an overview of the code base, the most important packages and classes, we will see how those classes work together in a particular part of the code base, which is the Monte Carlo tree search algorithm. So let's have a look at the AiZynthFinder class, which is the high-level Python API into a retrosynthesis algorithm. This class has a target smiles and also a target molecule property, which you can set in order to specify the target molecule that you want to break down. It has a config property that is set on instantiation, We'll see how that is done shortly. It has a reference to a search tree structure and also a reference to a root collection and an analysis class. And then it has mainly three methods. It has a tree search method, which you call to perform the retrosynthesis analysis. And afterwards, you call build roots to extract the synthetic root from the search tree. And then you have extract statistics to get some statistics from the search tree, the number of nodes, timings, etc. This shows how to use the AiZynthFinder class, and at the bottom there is some pseudocode for the tree search method. So you start with instantiating the class and giving it a reference to a YAML file. And as you saw previously, this YAML file will then be read by a configuration class loading stocks and policies into memory. And the next step is then to select the stock and the expansion and filter policies. When you have done that, you are ready to do retrosynthesis analysis. And you do that by setting a target smiles like this and calling the tree search method. And the tree search method is basically doing the following. It instantiates a search class. In this case, it's instantiating a Monte Carlo search tree class, giving it the target and the configuration, and then it loops over a number of iterations until the time limit is reached, or the maximum number of iterations is reached. And each time it calls the one iteration method of the tree class. And we will see what happens during that iteration in the next slide. But let's see at the very beginning here, when we instantiate the Monte Carlo search tree, what type of classes have been instantiated and what objects do we have in memory. So we have the AiZynthFinder class, which owns a Monte Carlo search tree object. This in turn holds a reference to a Monte Carlo tree search node, which is a node in the search tree, and it holds the reference to the root. That's the only node it really needs to keep track of. The node has an internal state, a Monte Carlo state, and the division here is based on historical reasons. They could be one class really, but they are separated. And this Monte Carlo state basically holds a list of molecules, a list of tree molecules. In this case, it's the root node, the very top, which represents the reference molecule. So it's only one molecule. See here. So that is the kind of relationship between objects that is in memory after we instantiate the Monte Carlo search tree, this line basically, before we do the actual retrosynthesis search. So as I just showed, the AiZynthFinder class is calling the one iteration method of the search tree class, and this performs one iteration of the search. And just to remind you what a Monte Carlo search tree looks like, we have a selection phase, an expansion phase, a rollout phase, and an update phase. And the code here is a slightly simplified, but not too much simplified version of the one iteration method. So first we have a call to a select leaf method, which takes care of the selection. Then we expand that leaf, and then we do a while loop, which is the rollout, we sequentially add more and more nodes to the search tree until we reach a terminal state, until the leaf is terminal. Then we have done our rollout, and we can do a back propagation, taking the score of that leaf node and updating the statistics throughout the search tree. And now we will look a little bit more into details on the different stages here. So first we have selection, and I will not talk so much about that. I will not go into any details, but basically we traverse the tree, selecting the most promising child at each level of the tree until we reach a leaf node. And at the first iteration, it will return the root node, and that's where we are in our algorithm at the moment. You saw at the start here that we just called, we instantiated the Monte Carlo search tree class, and then we called the one iteration. That's where we are now. So the selection phase has returned our root node. And then we come to the expansion. And to explain the expansion, I will use a sequence diagram. And I will spend some time just to explain what is in a sequence diagram. So we have a number of actors represented here by the class name, but they are objects in memory. They could be different objects of the same class, but I simplify it here. So in the expansion, we will deal with a Monte Carlo node, an expansion policy, and a retro reaction. Those are the classes that will be involved in the expansion. And where time goes from top to bottom, and the Monte Carlo node here is the leaf node. And the first thing it will do is to call the expansion policy to predict precursors. It will call the get actions method that we saw a few slides back. The next thing that will happen is that the expansion policy will do its thing. If it's a template-based method, which we assume here, it will create a number of retro reaction objects, and they will be returned to the Monte Carlo node together with priors, which in case of the template-based method is the probabilities from the neural network. And then the Monte Carlo node will create a number of lists. It will instantiate a list with children nodes, but it will not create any of those objects. It will just add none basically to a list. Then it will add or create a list of priors. It will create a list of visitation counts, which is the kind of statistics that is needed for the upper confidence bound statistics that will guide the search. But the important thing is that it will instantiate a list of children, but that list will basically just contains none. It will not create any children. And the reason for this is that this will speed up the calculations. So now we have done the two first lines of the one iteration method here. We have looked at the selection, and we have looked at the expansion. And at the end of the expansion, we have a Monte Carlo node with a list allocated for children, but those children are not instantiated. And the next thing is to do the rollout. And the first thing of the rollout loop is to select a most promising child. And we do that by computing the upper confidence bound score for each node and selecting the node that has the lowest UCB score and returning that. That's what will end up in the child variable here. So what we will look at now is the selection phase, because that is where the child node is created. It is not created when in the expansion, when we get back the retro reaction from the expansion policy, but rather when it's selected. And that will be clear. So let's look at that. So let's look at how we select a promising child. And we have even more actors here. We will have the search tree. We will have the Monte Carlo node, which is still the leaf or the root node. We have the Monte Carlo state, which is owned by the Monte Carlo node. We have a retro reaction, which was previously returned by the expansion policy and now stored by the Monte Carlo node. We will have to deal with 3 molecules, and we will see how the filter policy comes into play. So the first thing is that the Monte Carlo search tree will call the promising child, and then we will compute the UCB scores and return the child with the best reward function. And we do that by doing the following. We will take the retro reaction corresponding to the most promising child, and we will apply that reaction, which in case of the template-based approach, we will apply the template onto the target molecule. The retro reaction, when we call the apply, will create the reactant molecules by applying the template. And then it will return those reactants to the Monte Carlo node. The next thing that happens is that the Monte Carlo node will send the entire retro reaction to the filter policy and ask, is this a reaction that is okay? Can we keep this reaction? And let's say, for the sake of argument here, that nothing happens, the filter policy returns none, no exception is raised, it's fine. Then we come back to the Monte Carlo node here, and what it does is it will create a new state, copying over the molecules in its current state that is not the one that we have expanded on, and adding the new reactant molecules. So for the leaf node, it will take the current state, remove all molecules that we are not expanding on, which removes the root, the reference molecule, and then it will add all the molecules in that is in the reactants list of the retro reaction. And then it will take that state and use that as a state for a newly created child node. So it will create a new Monte Carlo node object that holds this new state with the reactants molecule. And now we have instantiated a child node. It corresponds to the child with the best reward function, and we can return that child to the Monte Carlo search tree. So let's look at what objects we have in memory, what classes have been instantiated after we select the most promising child. This is the last bit that we will look into the Monte Carlo tree search. So this was the classes that we had at the very start, before we started the one iteration. We have our AiZynthFinder class that holds a search tree which holds a reference to the root node, which holds a state, which holds a tree molecule. And these are the objects that have been added after we called select most promising child. The root node, corresponding by this one, now holds a reference to a child node, which is another Monte Carlo node, which holds another Monte Carlo state, which holds two tree molecules, which are the reactants of a retroreaction that was created by the expansion policy. And this retroreaction holds references to the molecule that is expanded on, the product, which is this tree molecule, and it holds a reference to two other tree molecules, which are the reactants. In fact, there should be a reference or a link between the retroreaction and the Monte Carlo node here, because this node holds a reference to this retroreaction, but for simplicity, I haven't shown it here. So these are the objects in the search tree that we are currently expanding on, and through cycles of expansion, selection, we will add more and more of the nodes, the states, the tree molecules, until we reach a stop criteria. So we have reached the stage where we have done a retrosynthesis analysis, and it's time for analysis. And now we will see how we extract roots and statistics from the search tree, what classes are involved in that. So what we will work from is the following complete Monte Carlo search tree. Of course, I write complete in parentheses here because this is just a subset of what would be in a complete search tree when we have done exhaustive search. But we have a few things that we already seen in previous slides. We have the search tree that holds a reference to a Monte Carlo node, the root node, which holds a state, basically a list of molecules, and this node has in turn a child node, which has a state with two molecules, and this node also has a child with a state that has three molecules. One of the molecules here is the same as in this state because it's this molecule that was broken down into these two molecules. So this is what we will analyze. I will first discuss the reaction tree data structure, which holds a synthetic root or a reaction tree. And it holds an attribute called graph, which is a network X directed acyclic graph consisting of unique molecules and fixed retroreaction objects. This is a bipartite graph with molecules and reactions, and you can get them with these two methods. It also has a few convenience functions for looking up the depth of some node in the tree if a node is in stock, and you can export this into a dictionary that you can save as a JSON, for instance, or as an image. But you can also read it from a dictionary structure. This is a way to serialize it. And there is a one-to-one correspondence between a reaction tree and the Monte Carlo search tree. And this is exactly the same structure that I showed in the previous slide, but as a reaction tree now. So we have a unique molecule as a root, and this is linked to a reaction, which is linked to molecules, and so on. So this is a directed acyclic graph. And the reason we have unique molecules here is to prevent cyclization. And because we know what the reactions are from the instantiation, they are fixed. You cannot, for instance, apply a template here. So now we will see how AiZynthFinder extract roots from a search tree, a Monte Carlo search tree. And it will do that in the build root method. And it will use these helper classes that I showed way back, the tree analysis class that knows how to extract information from a search tree, and the root collection, which is a container of roots. We will also use the scorer for the first time, which is able to rank roots and nodes. We will see what the Monte Carlo search tree is doing here and the reaction tree class, and then we will have these objects that will be a part of the reaction tree. So the first thing that AiZynthFinder is doing is to instantiate a new tree analysis class and a new root collection class. And when instantiating the new root collection class, it will pass the tree analysis class to it. And the root collection will use the tree analysis to fetch the top ranked new nodes. So these are the leaf nodes in the Monte Carlo search tree, and each leaf node corresponds to a reaction tree or a root. So it will fetch the top ranked nodes, and the tree analysis will fetch the complete graph from the Monte Carlo search tree in order to get all the leaf nodes, and then it will give those nodes to the scorer. And by default, we will use the Monte Carlo reward function. And now the root collection has top ranked nodes, and it will convert each of those to a reaction tree. And it does that by converting retroreaction to fixed retroreaction objects and tree molecule objects to unique molecule objects. Remember that retroreaction objects are the reactions that are returned by the expansion policy, which connects one node in the search tree to another node. And the tree molecules are the molecules that constitutes the state of a Monte Carlo node. And we will convert them to corresponding objects just to make them unmutable. So now at the end of this procedure, AiZynthFinder has a reference to a tree analysis class with top ranked node, and it can use that to extract more statistics about the search tree, and it also has a container of roots, the top ranked roots. So this is how the analysis is carried out. And then we have reached the final section of this presentation, where I put a few other bits and bobs that wasn't really fitting in well in the other parts of the presentation. And the first thing I will talk about is model training. So how to train expansion and filter models, and this is available in the AiZynthFinder training package. And it should be said that this is a less refined refactor part of the code base. It's quite primitive and not very robust, and the reason for that is that we haven't had any need for develop this to train new models. but there is ongoing work to do that, and hopefully there will be a better code released in the future. But for now, it provides some basic help to train Keras-based expansion and filter models, but they are all requisited on a high quality template library. So you need a library like this with reactions, atom-mapped reactions, retro templates created by, for instance, Artichiral. And if you have that, you can set up a configuration file and run a pre-processing script to featureize your data and then run the training. There is a lot of demand and a lot of questions on GitHub about training, so we see that there is a need for this, and we also acknowledge that a complete package for extracting templates and training models based on those templates is sorely lacking from the community, and perhaps we will be able to do something about that in the future. Let's talk a little bit about the testing of the code. So all code should be covered by a unit test, and we use the PyTest framework for writing the unit test. We aim for about 85% coverage, which I think is a nice and round number. I don't think we need to aim for higher than that, because it's hard to write good unit tests for the command line code and for the training code, for instance. And we also have type annotation that adds a lot of boilerplate code that is not covered, and I don't really know how to cover it with the unit test. But the important thing is that all non-trivial code should be covered by unit test. Next, I would like to talk about some development issues, things that you have to think about if you want to contribute to the code base, which I very most hope that you would like. So the code is auto-formatted with black, and it's PEP 8 compliant, and we have added type annotations throughout the code. And to ensure this, we have a continuous integration pipeline that runs unit tests. There is a couple of hundred different unit tests. We check the black formatting, we check type hints with MyPy, and we check code conventions with PyLint. And this is run using a GitHub action whenever you push to master. Requirements are managed with the Poetry package. Most requirements are installed with a pip-like install using Poetry, but RDKit, GraphWiz, and Poetry is installed with Conda. So we recommend to create a Conda environment. I know that there is an RDKit clone that is installed with PyPI, and if this becomes the official release in the future, we might change to a complete pip install. GraphWiz is not, of course, installable by pip because that's just binaries, so that we might still need Conda for that in the future. The documentation. We have API documentation auto-generated from the doc strings using Swings, and we augment this with handwritten guides. So, if you want to contribute and get started as a developer, it's quite straightforward, especially if you have worked with other open source projects in a collaborative fashion. You start with cloning the repository with Git. Then you create your Conda environment. We have one provided for development. You install the other requirements with Poetry. Then you can download public data models with the tool download public data. Then you do your magic. You do some cool stuff. You extend the package, you add the new modules and packages. Then you test your solution. And we will not accept any code that isn't tested with unit tests. And then you submit a pull request. And how do you use the software? Just a little overview of that. There is a simple GUI based on a Jupyter notebook and some widgets in a Jupyter notebook. It's simple to work and experiment with single compounds. And the advantage is that you can use the full power of the notebook environment to explore Python objects and to develop new features. I use it sometimes, but not a lot. There is the command line tool, which allows you to run predictions in batch mode. It's trivially parallelized, but in order to add new features, you have to put in a little bit of extra effort, but it's really good to run bulk calculations. And then finally, we have the Python interface. You have seen the usage of the AiZynthFinder class. And of course, this is possible to integrate into other code bases. And you truly have the full flexibility, but it requires more coding. So that's what I was going to talk about. So thank you for listening, and I hope you have gotten a better understanding of the code base of AiZynthFinder.